Hi everyone and welcome back. So right now we are talking about the powder properties and the characterization of powder to evaluate these properties. And we have seen one of the important properties, that is the particle size. And in past few classes we have discussed about the particle size measurement and the techniques which are used to measure particle size and size distribution. Okay. So now there is one more property of powder particles which is very important because this property controls many of the characteristics and properties of the powder and the material which is ultimately made out of the powder. Okay, this is surface area, and that is what we are going to talk about in this class as to how the surface area can be measured and what are the techniques available to do this measurement. So in this lecture we are going to learn about surface area analysis, and as I was mentioning, surface area is a very important property of powder particles because surface area is not only an indicator of the external condition of the particles, but it also often correlates with various properties of the particles such as chemical activity, catalysis, friction, adsorption, and also pressing and sintering, which are the two most important steps of the powder metallurgy process. Surface area, however, does not provide any information on distribution of properties, powder texture, or internal structure. Now, when it comes to measuring surface area, there are various techniques which can be used to measure it. However, by far the gas adsorption technique is the most widely used. And this gas adsorption technique is also known as the BET method, which stands for Brunner, Emmett, Taylor, after the names of the people who invented this theory. Now, the basic principle behind this technique goes back to the Langmuir adsorption theory or the Langmuir isotherms. So let us first talk about the Langmuir isotherms, and from that we'll get to understand about the basic principle behind this BET method. So the Langmuir isotherm is about the gas adsorption on a solid surface. So let's say this is the surface of a solid on which some gas molecules are adsorbed. So these gas molecules which are being adsorbed on the surface are known as the adsorbate, and the solid surface which is absorbing them is known as the adsorbent. Right? So the Langmuir isotherms describe the interaction between the adsorbate and the adsorbent. It basically describes the relation between the volume of a gas adsorbed on a solid surface and the pressure of the gas at constant temperature. So this is all about the relationship between the gas pressure and the volume of the gas which is being adsorbed on a solid surface. Okay. So let us see how these isotherms are derived. According to the Langmuir theory of adsorption, the adsorbent or the solid surface is considered to be a homogeneous surface having specific sites in which the adsorbate molecules can bind. And the binding of the adsorbate molecules on these sites, that means the adsorption process, is treated as a chemical reaction. Okay, so if you call this adsorbate as A, and this adsorbent as S, the chemical reaction can be written like this. So here A is in gaseous form, that is the adsorbate. S basically represents those sites or the vacant sites in which A can get adsorbed, and AS is the adsorbed complex which basically represents the occupied or filled sites. Right, so in the beginning when the gas is being adsorbed on the solid surface, some of the sites will be filled and some of them will be vacant, which can be represented in this manner. Right, so like this, where these red dots indicate the filled sites, so from here we can define a parameter called surface coverage. Which is generally written as theta, and that is basically the fraction of the occupied sites. Right? Now coming back to this adsorption reaction again, the forward reaction is the adsorption process and the reverse reaction is the desorption process. Okay, And each of these reactions will have their own reaction rate. So let's say the reaction rate for the adsorption process or the forward reaction is RA, and that for the reverse reaction or the desorption process is RD. All right. And these rates will be given as this. RA will be equal to Ka into the concentration of the reactants, where Ka is the rate constant for the forward reaction, similarly Rd will be given as where Kd is the rate constant of the reverse reaction. Right? Now this surface coverage theta is basically the fraction of occupied sites, as I said. So that can be given by the concentration of the adsorbed complex, or this term in reaction 3, and S represents the vacant sites, and therefore the concentration of S will be given by 1 minus theta, right? So therefore equations 2 and 3 can be written as this, okay? Now at equilibrium, the rate of the forward reaction will be equal to the rate of the reverse reaction, and therefore we can write this. Okay. Now this concentration of the adsorbate or the gas is basically the partial pressure, or you can say it is proportional to the partial pressure of the gas, and hence this can be also replaced by the pressure of the gas P, and from there we can rewrite equation 6 as and if we rearrange this, we can write this right, and here this term Ka by Kd is nothing but the equilibrium constant Keq. All right, and therefore we can write equation 8 as this, and we can again rearrange this as this equation. Right, so by all this rearrangement, we can get an expression for theta in the form of equation 9, and this is what is known as the Langmuir isotherm. This equation represents Langmuir isotherm. and we can also plot it, and you can also see the relationship of theta with the pressure of the gas, and that is what Langmuir isotherm is all about. As I said in the beginning, it basically describes the relationship between the volume and the pressure of the gas adsorbed on a solid surface. So you can see that at low pressure, this term is much less than 1, and therefore this can be taken equal to 1. On the other hand, at high pressure, this is much higher than 1. So this becomes approximately equal to this. Okay, 1 plus KEQP becomes approximately equal to KEQP, because this is much higher than 1. Okay, so considering these boundary conditions, now if you plot theta as a function of the gas pressure P, it will vary something like this. Right, so at high pressure, and this becomes equals to this, theta is 1. So what that essentially means is all the vacant sites are now occupied by the adsorbed gas. Okay, so in the beginning it was, fraction of sites only were occupied, but now as the gas pressure is increased, more and more sites will be occupied, and there will be a time at a particular pressure all the sites will be occupied. So that's when we say that the surface is saturated and a saturated monolayer of the gas has formed on the solid surface. Okay, so that can be represented with the help of this picture over here. Right, so in the beginning only a fraction of sites were occupied, as we have seen before also, and now at high pressure all the sites are occupied when theta is 1, right? And this is when, as I said, a saturated monolayer forms, which is just one atomic layer thick. And this is what the Langmuir isotherm basically describes: the formation of a saturated monolayer on an adsorbent surface. Okay, so we can say that a saturated monolayer forms when all the sides on the adsorbent surface are covered by the adsorbent gas. Right? And if Vm is the volume corresponding to the formation of the monolayer, then theta can also be written as V by Vm, where V is the volume of the gas. And from here, equation 9 can be rewritten as so we'll get an equation like this, which relates the volume of the gas to the volume corresponding to formation of a saturated monolayer. And from this, we can also write it in terms of P upon V. And therefore, a plot between P by V and P will give a straight line, the slope of which is 1 by Pm, and the intercept is 1 by Keq Vm. Okay, so this is the Langmuir Isotherm, which talks about the formation of a monolayer on a solid surface. And from that, the BT theory can also be explained. So in this case, we are talking about the monolayer, but this can also be extended to multiple layer, which is actually the case for the BAT theory, and that is what we are going to talk about next. But for this class, this is all I have. So with that, we come to the end of this class, but I am going to see you soon again. Thank you for your attention.